All right, and our next talk is by Roman Kuzmin, and he's going to talk about simulating quantum many-body phenomena with superconducting circuits. Roman.
Hello everyone, thank you for the introduction and inviting me. I'm glad to talk about our work. So I will describe our projects in UMD relating to quantum simulations of many-body problems with superconducting circuits. So let me start by acknowledging our team at UMD, which is a group of Vladimir Machuryan and graduate students, in particular Nitish Mehta, Raymond Mencia, and Nick Grabon, who contributed the most to the work I will talk about. And we got several collaborators in this area. So I will talk about an approach to quantum simulation, which is called analog quantum simulations, where the idea is that we design and build a physical device, a circuit. In this particular case, it consists of a cavity and a single qubit. And our goal is to build the circuit in a way such that its Hamiltonian is the same, at least in some parameter range, to a Hamiltonian of another target system, which can be some many-body problem, like a larger liquid with an impurity or something else. And an advantage of such approach is that, compared, for example, to universal quantum simulations on a universal quantum computer, is that we can make our circuits very large. Like, it may contain 10 to the 4 or even more elements, but of course, as the price appeals with some universality, and we need to build these circuits for each problem again and again. So let me start by explaining how this many-body physics actually appears in a circuit where excitations are essentially photons, which usually don't interact. So imagine a cavity, like a Fabry-Perot type cavity, which can host multiple modes and separated by free spectral range. And for example, if you populate some of the higher modes, mode J, it's a single photon, then the state will actually be in resonance to many other multi-photon states. So you can distribute an energy of this photon into two particle states, where, for example, one photon is in the mode below and one photon in the mode, the very first one, or one photon in the mode 2 down and photon in the second mode. Also, you can decompose the energy of this photon into 3 particle states, where you have one photon, for example, close to J, and then 2 photons in the lower states. Then there will be 4 particle states, and so on. And the number of such states grows very fast. For example, it's proportional to J cube for 4 particle states. So if this J is like 100 or something, there will be a lot of other multi-photon states which will be in resonance to this one single photon state. But if it's just a Fabry-Perot cavity, you don't care, because there's no interaction between all the states. So this massive degeneracy doesn't count. But things becomes different if you introduce a nonlinearity with the cavity, which is played in our case by a single qubit. So this qubit will introduce coupling between all these different states. It can actually, depending on a qubit, this coupling can be different. It can couple single photon states to 2 particle states, 3 particle states, and 4, or in different combinations. And now this problem becomes truly many-body, because all these states starts to interact with each other. And this description might remind you actually about quantum impurity models. So the quantum impurity model is a model where you have one single local degree of freedom quantum, which is coupled to a bus of non-interacting modes. And then the Hamiltonian contains this non-interacting part, impurity part, and an interaction. And this impurity part acts on some subset of modes M out of total number of modes M. And this is hard problem. It's actually its complexity scales with exponentially with m, and it appears in many problems. It appears, for example, in a description of quantum effect, impurities in lateral liquids, or dissipative phase transition, and also, as we learned yesterday in one of the lectures, it's actually a building block in a dynamical mean field theory. So today I will talk about several such problems by actually changing this impurity and show you how things are different for different impurities. So I will start first by introducing the bath, which is made out of metal material, which is called a Josephson transmission line. And then I will go through 3 examples. First one where we use fluxonium qubit as an impurity. Second is transmo qubit. And the other one is related to the previous one, similar kind of circuit, but which shows a dissipative quantum phase transition. So let me introduce this cavity which we use. So it's built out of 2 very long arrays of Josephson junctions. So each slide is connected, is composed out of a few like 30,000 junctions. So each rectangular here is aluminum oxide, aluminum junction. So it's like 2 aluminum films overlap, separated by an oxide, and they're connected in series. So they form 2 chains, and the whole system, you can think about it as a transmission line, where inductance, like a telegraph-like transmission line, where inductance comes from inductance of Josephson junctions, and this inductance can be actually quite large, much greater than geometric inductance from these films. And then the capacitance comes from this parallel capacitance between 2 lines. So such system can support waves where voltage oscillates in between of 2 chains and the current flows along the line. And these waves, you can introduce several parameters to characterize them. First, of course, it's the speed of light, which is slow because this inductance can be large, as I said. Also, impedance, which is also can be very large because of inductance. In fact, it can be greater than the resistance of quantum for Kuiper pairs, which is 6.5 kilo ohm, which is a necessary ingredient actually to create a strong interaction in the system. That's the reason why we use such an unusual cavity made out of Josephson junctions. So when you make it finite length, so here, for example, you have a shorted one end and it's open on the other end, the waves will be quantized, so there will be discrete set of modes. And we can excite those modes by coupling them to external RF fields using this antenna at the end. And the whole system, the whole chip is placed inside the 3D waveguide. Here is this device. It's 10 meters long, so you can see it. And we couple it to external RF signals and perform a spectroscopy. So when you do a spectroscopy, what you see a set of almost equally spaced resonances, which are the excitation of standard wave modes inside this transmission line, the section of transmission line. And you see that there are pretty, the distance between them is small, which implies that the speed of light is slow. Now, if you plot the frequencies of these modes as a function of wave number, you can measure a dispersion inside this transmission line, which is linear at the lower frequencies given by this slow speed of light. And then it saturates towards the higher frequencies, towards the frequency which is called plasma frequency. It's a self-resonance frequency of a single Josephson junction, because besides the inductance, which comes from the Josephson junction, there's also always a capacitance given by these parallel plates. And using this dispersion, we can extract parameters of the transmission line using this, fitting it to a simple expression with line. One useful feature of this metal material is you can tune its parameters in situ, in particular its dispersion and eventually impedance just by applying a perpendicular magnetic field. So you can, for example, tune this impedance through the value below resistance of quantum to the value above resistance of quantum, without introducing any disorder or complications. It works nicely. So let me now move to let me now introduce to those otherwise non-interacting modes, or actually very weakly interacting modes, and impurity. So now at the end of this transmission line, we place a qubit, which is fluxonium. So fluxonium, it's a small Josephson junction here with its own capacitance, and also shunted by a large inductance. So there is an additional array of Josephson junctions which introduces this inductance, and part of this inductance is shared with the transmission line, and that's how this qubit is coupled to a transmission line. So what's special about fluxoniums? So if you look at its energy spectrum at half integer flux quantum, so we can apply flux through this loop, the potential has this double well shape, and the ground and excited states, they are well separated from everything else. So fluxonium is very unharmonic qubit, it behaves more or less like spin. Also, it's currently the most coherent superconducting qubit. So when we couple the fluxonium to this line, so what happens? Fluxonium couples to many modes simultaneously, so it's kind of dissolved. You no longer have a qubit resonance, but what you have, you can introduce an effective Hamiltonian where this first part just describes the waves inside the line, and the interaction comes from which is coming from the fluxonium takes this three-wave mixing form. So what it tells you is that the fluxonium will induce the transitions where photon in mode K will disappear, and two photons in some other modes will appear. So what it does, let's look again at this diagram. So here on the left, I show you single photon states. So here is mode K. And then here, 2 particle, 3 particle, 4 particle states, just like I described you before, which contain many states formed by the single particle states. And this kind of term will introduce coupling between 1 particle state and 2 particle state. But also it will introduce, there will be some matrix elements for the transition between 2 particle states and 3 particle states if you keep the same low frequency photon, and between 3 particle states and 4 particle states and so on. So there's like a ladder of transitions possible if you populate a mode K. So another important point which I want to make here is those states, those multi-photon states, which I said they degenerate, and they actually might be not degenerate. So if you introduce a disorder in the system, which is always there, and also if you have some dispersion of those modes, the degeneracy is actually lifted, and you have some broadening. So they're no longer degenerate, but they are spread along the frequency, and eventually they actually form a continuum if you go to higher and higher photon states. So let's now look what happens in the experiment. So here I show you a spectroscopy data. So y-axis the frequency, and x-axis flux. So when flux is far away from half integer flux point, you see those lines. There are standing wave modes in the transmission line, which I showed you before. So the color represents reflection magnitude, just like a spectroscopy. So those modes they are not perturbed by a qubit. But when you tune the qubit, when you tune the flux, you change this resonance of the qubit, you will see that these modes become disturbed. So they shift. There is some shift, elastic shift, And this shift is introduced by a qubit transition, which is coming through those modes. Because you might also notice that actually it's not like a single anti-crossing, which you might expect if you pass one resonance across the other resonance, but many modes shift simultaneously. So it means that the qubit is coupled to many modes simultaneously, not to just one. But what's more interesting is that if you zoom in one of the lines, you will see a very interesting fine structure inside those modes. And so this single photon state actually anti-crosses with some other states, and this you see the spacing between these states is very small, much smaller than the free spectral range of the cavity. And those states are exactly two photon states. So using those effective Hamiltonian, we were able to reconstruct the spectrum and show that, for example, here the single photon states anti-crosses with two photon states with modes from 20 and 17 to 32 and 5. So, for example, if you take a card like this flux, just measure the spectrum, you are in a situation where you are trying to calculate a mode 37. This is mode 37, but actually it couples to 5 other two photon states, but it couples coherently. So it's goes there and it goes back. So that's why you see it's like anti-crossing. You can find a spot in the spectrum where actually the anti-crossing is even denser, and those are 3 photon states. So if you stop at this flux, so what happens? You're trying to calculate mode 41, but it couples to 2 photon states, and these 2 photon states is coupled to several 3 photon states. But then it's still like anti-crossing, so it's a coherent coupling. So the photon is trying to propagate along this tree of states, like in the Fock space, but it fails because there is a disorder in those states. And this is similar to a situation which was considered a long time ago, where you are trying to analyze generalization of electron in a quantum dot. So when there is no continuum states, the generalization of an electron is a hard problem, and it's actually it's this paper by Schiller. It's one of the first developments in the field of many-body localization, and that's one of the illustrations of many-body localizations. So let me now talk about my second example. So now we will change the impurity. The transmission line stays the same. It's non-interacting photons, but the impurity is different. And now it's more like a transmo type qubit, so which consists of a Josephson junction shunted by its capacitance. And here it's made in the form of a Scatte, such that we can tune this Josephson energy of this qubit. So let me explain a little bit more how to think about these Josephson junctions. So this qubit or Josephson junction can be described by a phase difference across the Josephson junction, and you can think about its physics like a behavior of a particle in a cosine potential. Cosine potential in phi in this phase given by the Josephson relation, where Ej is the Josephson energy. And then if this potential is deep enough, there will be some levels. So if there are 2 levels, you can get a kind of a qubit. So there will be a resonance transition between ground and excited state, given by, again, this Josephson energy. Now, if this potential is not deep enough, or if your charging energy, which plays the role of 1 over particle mass, is large, so the particle is light, so it can tunnel between wells. And what it does, so this tunneling is called quantum phase slips. And what it does, it introduces broadening to the levels, which you can also think like dependence of the energy on a conjugate variable, which is charge, which is quasi-charge, which flows inside the junction. And now, so when you have this phase slips, so the way to model the physics, then we can write this effective Hamiltonian, where we again have non-interacting photons, and then this cosine Q term, where Q is this quasi-charge, it's a dual variable to space. But this quasi-charge is an operator, and it actually contains superposition of all these creation and annihilation operators of the modes inside. And now, because it's a cosine, you can imagine that if you plug in this Q here, there will be terms which are like 4, 6, and so on operators, where you destroy photon in mode J and create 3 others, or 5 others, or 7 others. So then this kind of impurity has a different connectivity in this Fock space. So what it does, it connects your single photon states to straight away to 3 particle states and 5 particle states and so on. And because it has this kind of stronger connectivity, and also because there are many more states in 3 and 5, so the dynamics is actually different. So here on the left, I show you a spectroscopy data where I show you positions of the modes in a measured device. And if you just zoom in a line within the line width of the mode 47, you will see that there are almost continuum spectrum of multi-photon states, which is 3 or 5 photon states. And these states are formed by more or less all other states in the system. So what happens in this situation is that you place a photon in mode 47, and it goes to 3 or 5 other states, and then those photons will go again to 3 or 5 photon states, and then actually a photon is lost. So here the dynamics is different. You don't see any more those finite splittings, but what you see a broadening of your resonance. You're trying to put a photon in one of the modes, and here I show you a piece of spectroscopy, where again these resonances, there are standing wave modes in the line, in the transmission line, and you tune a resonance of the qubit through them, and you again see the shift, which is kind of trivial. It's just a shift of an LC oscillator. But what is more interesting is the line width of these modes become broader, which is depicted here as a color, and actually it's converted to photon loss probability around chip. And this photon loss probability can be quite large. It can be almost 1, so it means that every single photon you will put in this mode disappears. So if you take, for example, a cut at one particular flux, so you will see that there is this extra dissipation coming like on top of some background loss which we know. And this extra dissipation, this comes from this inelastic scattering introduced by the qubit, and it's actually connected to a self-energy of interacting Impedance function, which we also heard yesterday. That's the way to measure, to get an access to this Impedance function by measuring this photon loss probability, which is given by line width of the mode. And in fact, if you focus just on this inelastic rated resonance, you can plot, it gets plots like this, where this is this elastic rate is function of resonance frequency for 4 different devices. And with the help of our theory collaborators in this particular regime, where we have this small parameter, we were able to get an analytical expression which describes pretty well our results. And there are no adjustable parameters. All parameters are measured, and the uncertainty measurement gives this theory lines some lines. So in this way we can actually. But what's nice about these systems is now we can change this impedance even in situ and move to and go away from this regime where there is a small parameter, and now there is no theory. And this kind of data, because we already verified it with analytical expression, it can be used to test, for example, your numerical algorithms, or maybe test some digital quantum computers, which can simulate the same problem And that's to the question of verifying quantum simulation. So now in the last time I will talk about my third example, which is related to the previous one. It's also a single Josephson junction at the end of the transmission line. But now we'll make it a little bit smaller, such that there's only a single resonance inside. And there is this very interesting prediction, which was around for almost 40 years already, that such system should go through a quantum phase transition as a function of impedance of the environment. So when you connect this Josephson junction to a resistor with some impedance Z, and if impedance is small, so the dissipation, it means the dissipation is large. So the dissipation actually suppresses the tunneling, so the particle is fixed, is sitting in one well, and the phase is well defined. It means the junction is superconducting. But when dissipation is small, meaning that the Z is greater than this resistance of quantum, the phase flips are no longer suppressed, and the junction is in insulating state. And this phase boundary happens at resistance of quantum, which is given by this just fundamental constants, and it doesn't depend on the junction, on this ratio of EJ over EC. And as I mentioned, it was predicted a long time ago. It's not a hard problem to calculate, and actually there are multiple works in different numerical and logical methods to establish this transition. But the problem actually is that there was no experiment which could prove that this transition exists. And actually, some experiments which claim that there's no such thing. So what we do here, we use this Josephson junction transmission line as our resistor, and the advantage of such circuit using this circuit instead of just a method thin film resistor or something is that we can build it and have an access to its internal degrees of freedom, which are those standard wave modes. And the idea, here is this transmission line and a small Josephson junction at the end, which is again in the form of squid. And here you use squid in the way so that because the junction is very small, so when you tune flux to the half integer flux quantum, you can think that the J is essentially zero. So it means that at half integer flux quantum, you kind of remove the junction out of the circuit, and then when it's not, the flux is not half integer, you put it back. And now, so in this formulation, the question of transition can be reformulated. So now, so we want to know is it a superconductor or an insulator, and now it's a question of a boundary condition for the waves inside the transmission line. And if you're asking this question of the finite frequency, it's actually a question: is it a inductor or a capacitor? Is it short or open? And that's something which we can say by looking at the modes inside the transmission line. So let me show you an experiment, the result. So here again, it's a spectroscopy, just one mode, around 6.5 gigahertz. It's a function of flux. So here, as I said, at half integer flux quantum, we can see that the junction is not there. But at zero flux, you put it back. So you put it back, a mode shifts to the right. And this shift to the right is what you expect from an inductor. So when you have an inductor as your boundary condition, it introduces a phase which is positive and it shifts the modes to the right. And it's not a surprise, I say that junctions are used as an inductors. But this is a situation where this Z over Q is less than 1. If you fabricate a device where this Z over Q is greater than 1, you see the opposite behavior. The mode actually shifts to the left, and that's exactly what you expect from a capacitor, which introduces a negative phase shift, so the modes shift to the left. So there is a transition somewhere between 0.5 and 3, and we can look at it more closely by using this trick where we tune in situ the impedance of the line. So here on the top, I show you a position of one mode around 7.5 gigahertz with some corrections as a function of flux. And you see this flux now goes to some higher values, and at these values you start to tune also the impedance of the transmission line. And these oscillations is the same oscillation as you see here. But what happens is when you see that this oscillation disappears and then appear again, but with a different shift. So this data is the line basis was measured simultaneously, and you see here you have maximum corresponding to maximum, and here minimum corresponding to maximum. So we see the same transition between positive and negative phase shift, which happens exactly around Z over Q equal to 1, plus minus 0.1, which is uncertainty of our measurement for impedance. So the transition is indeed there at the value which was originally predicted almost 40 years ago. And it's not the end of the story actually, because if you notice, it's not only the line that shifts, but also its line width changes. It becomes broader. This broadening has the same nature as I was describing before. It's just this photon disappears to the other states. And if you measure this broadening across the transition, just at one frequency, nothing special happens. But this broadening, because it contains information about many body properties, it's actually a very useful tool. But the way to look at it is it's a function of frequency. So as a function of frequency, you can plot this broadening and normalize it by free spectral range and small Josephson junction area. You will see that, for example, these two devices, orange and red, the data align on each other, even though the junctions are different. Actually, the area of the junction is twice different, which means that the EJ we see is 4 times different. But they align to each other, and they follow this simple expression where which is just a frequency with some non-universal scaling given by this Z over Q parameter. And so the transition also happens in this inelastic rate, and it happens in the way that the slope of this line changes when you change this ratio, and it changes to something like negative, but it's almost negative, but it's limited by the temperature actually. Yeah, so this simulation allowed us to see this transition in a new, conceptually new way, which is, I think, very good. So let me now conclude by summarizing by saying that so we have this a platform many Josephson junctions forming a transmission line and various qubits which can be used to solve multiple problems. And I demonstrated you approach to new approach to experiments with many body localization. Also, I showed you how this simulation of a strongly correlated problem can be used potentially to test some other algorithms, and also demonstrated you dissipative quantum phase transition, which was a hard problem before. And all this, of course, can be developed and moved to various directions, introducing some dynamics of like branches or many other things. Thank you.
For your nice look at in your spectroscopy data, do you did like anti-crossings? I remember that there was a coupling map in the right side of this slide. So, I mean next slide. Yeah, like the right side.
Mm-hmm.
Are those data are obtained from the experimental data or are really direct curve?
So this is from experimental data by matching it to. So basically, it's kind of simple because you know the frequencies of all your modes. You can measure them, and then you use those frequencies to construct two photon states, for example, just by summing all of them. And then you put them on your spectroscopy, and you see that actually where there is this photon, two photon states, you see an optic crossing. It's just like by finding these numbers, it's pretty simple. You just sum the frequencies.
How tunable are the parameters in your Hamiltonian?
What parameters are tunable?
Yeah, and how tunable are they?
Right. Yes. So if you talk, for example, about some you can tune multiple things. First of all, you can tune impedance of this transmission line, as I showed, by either in fabrication stage or with a magnetic field, and it affects multiple things, but most, for example, coupling. It will affect the coupling between the two. For example, for fluxonium in situ, you tune flux grid, which for example changes in G, and that's it. But you can play with fluxonium to change fluxonium and turn on the application state.
All right. If there are no more questions, let's thank Roman again.